Good afternoon, it's Abdel-Razzak Merheb again. Now I will be presenting my second group's presentation entitled Simulation and Implementation of an Analog Simulator for Quadcopters. This is the plan of my presentation, with an introduction, move up to analog and digital simulations, and end up with some concluding ideas and future work points. I bet everyone that worked with Simulink has faced this error. It is the infamous singularity error, and it happens whenever we have fluctuations in the signals or unstable systems. Simulation is very important in control engineering and in other scopes. For control engineering, it helps us to develop robust and reliable controllers. It allows us to test, to design and test controllers even without building the systems themselves. It allows us to extend the tests even beyond the normal conditions. The first flight simulators were actually flight trainers, were very simple mechanical systems. It's not until the 30s and the Second World War that electronic systems, electronic simulators were developed, and these simulators were fiddle in presenting the outputs or the actions of an airplane. Since the 70s, digital simulators became dominant in the flight as flight simulators. Now, in this study, we are proposing the design of an analog simulator for quadcopters. Actually, here we are not trying to resurrect or to revive all technological zombies, because these techniques have perished a long time ago. But analog computers have low power consumption and high efficiency, and analog simulators are more realistic, especially under extreme conditions, than digital simulators. Actually, while looking or making our research, we found a company in the US called Mythic, and this company manufactures artificial intelligence chips, and these chips are analog chips. Now let's move up to the quadcopters. Quadcopters are UAVs, unmanned aerial vehicles, with 4 rotors that help them to fly and hover. As you can see at the right hand of the screen, we can see the schematic of a quadcopter with its 4 rotors, and the variables are here: roll angle, rotation around x-axis, pitch angle, rotation around y-axis, and the yaw angle, rotation around z-axis, and we have also the height. At the left of the screen, we can see the nonlinear dynamic equations of the quadcopter. These equations can be linearized, seeking simplicity, in order to end up with the linear model of the quadcopter. These equations now are very simple, and they include only the control input, a disturbance, and a variable related to the quadcopter itself. For example, for the z variable, we have u1 as the control input, f omega z as the disturbance, and m, which is the mass of the quadcopter, and that affects its the quadcopter motion along the z-axis. For the analog simulation, as a simple example, we have the mass spring damper system that we can see its dynamic equation here. This equation can be implemented easily using Simulink. As you can see, we need only a subtractor and 2 integrators, and these subtractors and integrators can be modeled using opamps. As you can see at the right of the screen, we have the adder, subtractor, and integrator modeled or made using opamps. The equations, especially the linear equations of the quadcopter, can be modeled using opamps as well. Why? Because, as you can see here, for the z equation as an example, we need a subtractor, a divider, and 2 integrators. For the PID controller as well, we need a subtractor, an integrator, a differentiator, and an adder. So we implemented the equations of the quadcopter, as you can see here, in LT-SPICE. This is the equation of the height, the Z variable. We implemented the PID controller as long as the equation itself, and the gains are shown on the screen. Similarly, for the roll and pitch angles, we modeled them in LT-SPICE, and the gains are shown. And we have the same thing for the yaw angle. Now the results of the simulation, the result of the height is shown now. The blue line is for the input and the green line is for the output. Maximizing the angle here, the figure here, we can see that we have only 3% overshoot, and the rise time is 1.3 seconds, which is very good. And the error is the steady state error is about 0.023 volts. Similarly, for the roll and pitch angles, the input here is a sinusoidal signal with a frequency of 0.5 hertz. The magnitude of the input is 0.2 volts, so the error is only 0.01 volts here. Similarly, for the yaw angle, the input is a square wave. As you can see, we have no overshoot, and the rise time is 0.2 seconds. The steady state error is very small. It's about 0.008 volts. Now we implemented the same equations, but now on using breadboard and actual electronic components. As you can see here, the height and yaw angle equations are implemented. As you can see, the PID controller also is implemented using opamps. Now the height and yaw equations are very similar, so we had the same circuit. But for the yaw angle, we changed only some resistors in order to end up with the yaw angle simulation. Similarly, for the roll and pitch angles, we implemented them on the breadboard. Here also the both equations are very similar, and we end up with replacing some resistors in order to in order to transform the roll angle simulation into the pitch angle simulation. The gains are shown here as well. Now these are the outputs or the response of the height simulation. The input is a square wave with magnitude of 5 volts. So as a result, we have a rise time of 0.1 seconds. And the error is very small. Similarly, for the pitch and for the roll and pitch angles, the input is a sinusoidal signal with 0.5 hertz as input, as a frequency. The magnitude error is 0.01 volt only, and the phase shift between the input and the output is 23.4 degrees. For the yaw angle, here also the input is a square wave, and the errors, the steady state error is only 0.01 volts with 0.1 second as rise time. Now these are the simulation, the analog simulation of the linearized equations. The nonlinear equations are implemented only in Simulink, and these are the gains used. The results of the nonlinear equations are comparable with the analog results and analog simulation. Now, using the analog simulation in control engineering is very important, especially in designing fault-tolerant controllers. Now, fault-tolerant controllers allow the system to keep going, to keep doing its task, even if it has a fault, for example, in a sensor or even in an actuator. For quadcopters, fault-tolerant controllers are very important because quadcopters are under actuated systems, which means that whenever a fault strikes any quadcopter, it will fail and crash. So implementing fault-tolerant controllers is very essential, but very hard. Why? Because while flying, the onboard computer of a quadcopter has to control the quadcopter, and at the same time has to run in parallel a simulation of the quadcopter. Why? Because by comparing the output of the simulation with the output of the actual quadcopter, the controller can detect any anomaly or any fault. This requires that the onboard computers should be very complex and very fast, because they have two tasks: control the quadcopter and running a simulation. So if we can use a quadrotor analog chip, it will be possible to use very simple and very cheap onboard computers to control quadcopters, and these controllers will be fault-tolerant controllers. Now, to sum up, we have implemented the simulation, the analog simulation of a quadcopter using LTSpice and using actual components on breadboard. Now, obtaining the exact value for the components was slightly hard because, as you know, it is it is impossible to find a resistor with the value of 1.35 kilo ohms, for example. Secondly, the characteristics of the resistors, the electronic components, change according to the environment, for example, excess heat and so on. So the characteristics of the resistors will also change, and this includes or induces model uncertainty to analog simulation, which is good because actual quadcopters have also model uncertainty. If you would like to compare different simulators, the Simulink, the Simulink simulator had the best results, but it uses the nonlinear equations. Both digital simulations, I mean here the Simulink simulation and the LTSpice simulation, get running errors if the hardware gains are used. For the analog simulation using breadboard, we have always an output. Okay, even though this output may be saturated or not realistic, but we have always output, which is not the case for digital simulations. Now we are thinking of implementing the actual equations of the quadcopter, which are the nonlinear equations, using opamps. As well, the analog simulator will be put also under extensive test, under extreme input values, for example, very fast values, very different temperature conditions, and so on. And we will be able to evaluate the performance of the analog simulator. And we will use instrumentation amplifiers instead of operational amplifiers. We are thinking to merge both methodologies, the digital and the analog simulators in the future, and to implement nonlinear controllers instead of the very easy PID controller. For example, if we implement sliding mount control, which has inherent robustness, I think the controller will be better or more robust, and we call computer engineers to develop analog chips, analog quadcopter chips using VLSI, and we extend also our call to mechanical engineers in order to develop mechanical simulators to test and examine newly emerging systems using old techniques. This is everything, and thank you very much.